questions about your homework?
Very well.
15 and 16 on the AROC sheet. I don't know where my sheets are. Give me the, can you call it out to me? Oh, it's a word problem? Oh, let me see it. All right. I'm on 15 on the AROC sheet. Yes. All right, so this says that X is the month, and F of X is the temperature. Find the average rate of change from March to August. March to August. So if X represents the month, that means January is going to be 1, February is going to be 2, and so on and so forth. Okay? So in March, that means X is 3. August would be what? 8. So all I'm doing is AROC on the interval from 3 to 8. So I'll do F of 3, and I'll plug that in, and I don't know what you get. Thank you. 46.1. And then I'll do August, which is F of 8, and you get 64 point what? And now I just do AROC. So I do 64.1 minus 46.1 divided by 8 minus 3, which would be, what is it? And so if I put that as a decimal, but I do want you to think about units for just a minute. This is a rate of change. Can you think of what the units would be here? So rate, I'm thinking that per, right? Think about like a slope. Degrees per month. This would be degrees per month. Per month. Your units up top are degrees, your units on the bottom are months. Yeah. Per month. Yeah. Yeah, this is important. Well, because when you get to AP Cal, if you don't put the units, they don't give you your answer point. So it's better to be in the habit of it now than later. All right, and then the next one asked you, I think, the average rate of change from the beginning until the maximum or something like that. Can you give me that equation? And so it said from the beginning, which would be when X equals 0, up until the maximum, it wanted the average rate of change. See, because this is a quadratic that opens down, my maximum's happening at my vertex, yes? So I'm going to find the vertex first is what I'm going to do. So the vertex, of course, the X would be opposite B over 2A. So that's going to be your 0. Whenever you do F of 0 and you plug it in, you get 6. Because at time 0, it's starting, so it's up 6 feet and it goes shoop and shut off. If you plug in 0, right. But for the maximum, I've got to actually calculate it. So this would be negative 120 over 2 times negative 16, 3.75. You could go second trace and find the maximum. Yeah. But I've got to plug this back in so that I find the y that goes with it. 3.75 squared plus 120, 3.75 plus 6. I got 231. Is that what y'all got? And so now I'm doing AROC from 0 to 3.75. So 231 minus 6 over 3.75 minus 0. What are my units? Feet per second. Yeah. Yes. Lisa, could you have this on a test? If you put it on the calculator. Plugged it back into the original equation. So negative 16 times 3.75 squared plus 120 times 3.75. No, I think we're going to save that for tomorrow. No. Plug and bring it to you. All right, y'all done? Yeah. What's the problem? Zero to 7, is that right? All right, so f of 0 would be cube root of negative 1. Cube root of negative 1 is just negative 1. And then f of 7 is the cube root of 4 times 7 minus 1. 28 minus 1 is 27. So what number times itself 3 times 3 is 27. So then your A rock would be 3 minus negative 1 over 7 minus 0. 4%. No.
It was like a 5-page paper. How do you write a 5-page? Davis, he has returned.
Talking through this because you have enough information to be able to do these on your own, but we spend a day because these are so important in CCAL, and you have to know every single one of these parent functions because we are going to start transforming every one of these parent functions. In Algebra 2, we focused mostly on linear and quadratic and absolute value, and those are on here, but then we start adding a lot more on here. So I'm going to go through and give you the parent function. I'll run through a complete analysis of at least one of them, and then I'm going to leave you to it on your own, because you should be able to do the rest of the analysis. All right, so we'll start with linear. Remember, parent functions are before any transformation has happened to them. And transformations we will talk about tomorrow. That's where we start sliding left, right, up, down, stretching, shrinking, flipping, all that good stuff that help us to easily graph a function. Ready? Who knows what parent function linear looks like? F of x equals what? X is x. F of x equals x. The graph is already there for you. No. No, F of x. But don't ask me if you don't want my answer. All right. The only thing that's new, and not even new, but I did not think about telling you before, to review was end behavior. Do y'all remember end behavior? So I need however many arrows you see on your graph, that's how many pieces you need to your end behavior. Okay. Most of the time it's just a left and a right, but some of them, like the reciprocal function, would have 4. That's right. They would have 4. And I'll probably do that one with you whenever we get there. But the end behavior on this one, as x approaches infinity, so as I look to the right side, what is the graph doing? It's going to infinity. And then as x approaches negative infinity, so as I look to the left side, f of x is doing what? Negative. Okay. So there's your end behavior. And you can just put on here if you want to. And you should be able to answer all the rest of the information there for that parent graph. So now let's just run through some of these parent graphs, what they are. If there's anything you don't know about them, stop me as we go, and I can answer those questions. There's a few things that oh. Absolute value, what's the parent graph look like? Or what's the parent function equation? Good. How about quadratic? Okay. That's okay. Right now, I'm just going to go through and give you the parent functions for each one. And then if there's something I think you might struggle with doing, I'll talk you through it. But you should be able to do. This is all we're going to do today, or that's the plan right now. Yeah. Yeah. All right, how about quadratic? What's the parent function? X squared. Cubic. Funny. Yeah. This is why we're kind of rushing through these first ones because they're super duper easy. Square root. I should have left the graph blank and let you give you the parent name. I do want to say something about the square root real quick, especially in regards to in behavior. I told you however many arrows, that's how many ends you need, right? This one starts at 0, 0 and goes off this way. So my right end is really easy for in behavior, yes? As x approaches infinity, what does f of x do? But as x approaches, I never approach negative infinity. I just approach a point. What is that point? 0. So as x goes to 0, f of x also goes to 0. Because it just ends at this point right here. Cube root, what's it look like? Parent function. That's right. It's got the little 3 that sits in here. Be very careful when you write it. Do not write it like this because that's 3 times the square root. So make sure it's really little and it sits in the radical. Yeah. I hate to be that guy, but I will. Reciprocal is a new one. 1 over x. That's exactly right. It's we will do a lot with this here in the next unit. This one has 4 pieces to the end behavior because I have 2 different asymptotes. For this one, this is a vertical asymptote as well as a horizontal asymptote. So there's 2 different. Oh, just write rule. Okay. Y'all have any questions about the reciprocal one? These are just straight enough. You want me to do in behavior for that one? So in behavior on this one, remember 4 parts. As x approaches, and I'm just going to start with positive infinity because that's generally where I start. F of x approaches, you tell me what it approaches. 0. 0. Okay, so x, y. So as x gets really big, y gets closer to 0. Here's where things are going to get a little bit different. We have not learned this. This is new. I think it's new. I might have covered this one. As x approaches, this time I'm going to say 0, but notice if I just say 0, it's different depending on the side you're on. Does everybody see that? So I put a little teeny plus above here. Did I do this with Algebra 2? Okay. This tells me if I say x approaches 0 with a little plus, that means from the right. So if I said a little teeny minus, what do you think that means? From the left. From the positive side or from the negative side. So if I said, what's the end behavior as x approaches 0 from the right, what would you say? Graph. Positive infinity. It's going up. This is your axis, right? As I approach 0, so as x gets closer to 0 from the right side, the graph goes up. Then you have to do it for the left. Remember, the number of arrows is telling you the number of pieces. So as x approaches 0 from the left this time, what is my graph doing? Negative. There's 4. That's right. Last one. I ain't got it yet. I'm coming. All right, as x goes to negative infinity, so as I look as far left as I can, it's approaching 0. No, because that one's not. You only do from the left and right whenever you're talking about the y. Yes, sir. Oh, it gets good. We're getting to the good stuff. You can, it's not doing good. Exponential. He said, can Dozier and I protest? I said, you can, but it won't do you any good. What? What are y'all talking about? Does anybody know what graph that is? What that's the graph over there? What's the parent function? You're close, but we give it a base of 2 when we do this. That's the parent. There is an asymptote. Where is the asymptote on this one? No, look at the graph. An invisible boundary. So yes. This one's got. The asymptote, it hugs it, it gets really, really close, but it never crosses or touches. Yep. I've only got 2 ends, right? A left and a right end. As x approaches infinity, what end am I looking at? The right end. What does the graph do? It goes up. As x approaches negative infinity, you're exactly right. The graph gets closer and closer to logarithmic. I don't have any. What? I did not.
I heard you.
He said you can't protest. You can't protest.
Hey.
Thank you, Miguel.
I heard you say.
The greatest industry doesn't have any.
I heard you say.
All right, logarithmic parent function. Yeah. Did y'all not do any logs in this? You did logs.
No, we did not.
We didn't do those.
We did not.
But y'all did logs. We didn't do the earthquake project now. All right. We'll do a unit on logs. There's no worries. We'll get to some logs. If you don't know, let me just say this. Did y'all do logs in Ms. Otto's class? Logs are just another way to write exponentials. The little number on the bottom is your base. What it equals is the exponent. And so we can change forms between logarithmic and exponential. A lot. Okay, so let me just run through what the graph looks like, and let me run through a couple things about logs. Okay? We'll hit logs hard and heavy here real soon. If I have, let's say, log base 2 of 8, that's asking me what power do I have to raise 2 to in order to get 8? And that would be 3. Okay, it's just logs always equal exponents. It's another way to write an exponential. Whenever we need to solve, if I have something that I can't solve, maybe I have 2 to the x equals, I don't know, 15. Okay, I have no idea what x is, but I could change it to logarithmic form and evaluate. Log base 2 of 15 equals x. Makes it easy. You can, yeah, we can do it on the calculator. But they help us to, if there's no base, in which case, this one has no base, right? We see that? There's no base. What's the implied base?
1.
10.
20.
Thank you. 10. If there's no base, it's a base of 10. Now, here's the other thing that you need to know. When graphing them, logs are the inverses or the opposites of exponentials. So think about what inverse means. Inverse, remember when we did inverses? It switches x and y.
The same thing.
So logs, instead of, exponentials look like this, right? Instead of looking like that, it's flipped on its side. It has a vertical asymptote. And then it comes in and hogs the asymptote from that direction. That's the parent function, yep. Okay, what do you think it is? Let's go both ends. As x approaches infinity, what does the graph do? Okay. What's the other end? As x approaches what? It's not going to negative infinity. What's it going to? 0, but only from the positive side, right?
What's the positive side? The positive side is the right.
The right side, only from the right side. This one's only going to have 2. What's the graph do? 0. Yeah, because it's coming in from the right. If it had done this, I would say 0 from the left. Oh, sorry, it's negative infinity. Sorry. Yeah. Sorry. Sorry. It is, but it's going down forever. As x approaches 0 from the right, f of x goes down. Kenzie, get together.
Wait,
I'll do that again.
Do it, bro. I was the only one in my group who writ one, and we had to put mine up.
What did you writ?
I read a priest. Whatever, writ, right.
What are you even talking about? Are you speaking English? A Preces? What does that mean? Is this an actual thing? A Preces? No, it's not.
No.
Oh my gosh.
It is real.
Okay. All right, here we go. Yay or nay on logarithmic? Yay. Greatest integer. Yeah, you have. Does it have them? Does it?
No.
Does it?
No. Like, yeah, I have them available. No, it doesn't. Oh. No extruders. It doesn't have any.
That's one of the things you have to, yes. Max or min?
No.
Maximum.
No, because it's always going up or it's always going down.
That's right.
There's no.
That's right.
Shut up!
Alright, what is greatest integer?
All right, I don't want to move on from this if y'all are not ready to move on from this one. You don't know what any.
Okay, this one last year.
This whole back page is probably new to everybody.
No, I know.
Even when we got to logs, though, we didn't graph them. I know we didn't get to graph them. All right. Whoa. Oh, shoot, bro. Okay, this one is hard. Are y'all ready? This is the staircase. This is, even though it says greatest integer, it rounds down. Okay, and I want to take just a minute because we used to focus on this in Algebra 2 a lot and we kind of got away from it. So I want to take just a minute because it comes up every now and then in calculus. I want to take just a minute to explain what this does. This says whatever value x has, round that down to the closest integer below it to get y. That's what it says. So if I have 1.2, what's the closest integer below that? 1. So at 1.2, I'm at 1. If I'm at 1.7, it's still 1 because it's always rounding down. So it's still at 1. And in fact, all the way up, if you look, you notice how it's a solid dot here, but then an open dot here? That's where it jumps, okay? So all the way here, it's 1. Even 1.999999999 is still 1. But at the point that you move to 2, it jumps up to 2. And then all the way up until I'm right before I hit 3, it's still 2. And then at the point where I move to 3, that's when it jumps up. Yes. Okay, so let me ask you this. Is this a function?
Yeah.
Why?
Because this one solid on is non-solid.
If I did a vertical line right here, does it hit the graph more than once? No. It hits the solid dot and an open dot. It's not included. Open means it doesn't include it. So it's only hitting right here. So it is a function. All right, these are hard. I know these are hard. Y'all look like you are fixing to fall asleep. Some of you are falling asleep sitting straight up. Okay. Yeah. I do want to run through the analysis of this one with you because it's hard. Okay, so y'all stay with me. Domain on this one, what is it? Yep, all real numbers. Name for the company. How about range though?
All real numbers.
All right, let me show you how to write this. This is new notation. Do y'all need to stand up and stretch a minute or something?
Yes.
Okay. Differently in our notation, and here's what we're going to do. I'm going to say X, and then I'm going to do this funny little symbol. That little symbol means is a member of. And then I'm going to do a symbol for integers. The symbol for integers, the big fancy Z. Now, oh, this should be Y, y'all. This should be Y, sorry. Now, if you do not want to do it this way, this is the easiest way to do it. Yes. You can also say Y is ... -2, -1, 0, 1, 2, ... This is the most accepted way. But here's, well, you'll see in just a minute why the first way is better for what we're doing. Yeah.
Yes. What do you think I said? Yes.
No.
Is this a continuous function?
No.
It's a jump. It's got a jump. It's got an infinite number of jumps. The jumps occur at every integer. Okay, we're chilling. All right, I think you should be able to do the rest of them. It still, as x goes to infinity, y is still going to infinity. And as x goes to negative infinity, y is still going to infinity. You can ignore the increasing, decreasing interval part because it's always constant. It's always constant, so there's none for that. No, just for this one. Yeah. Yeah. There's no increasing interval and there's no decreasing interval for this one. Because it's a constant line.
Get them right either.
I got 2 of the book questions right.
I would give an answer.
You would collectively as a group tell him the right answer, and then you pick whatever you wanted.
And that's why we got second to last.
And it was always the wrong answer.
We lost against the.
Because Miguel was at the end of the table, so he had to submit all of our answers.
And you have to know, but we will get to that very, very soon. Right now, we'll stop with sine and cosine. I'm not even going really deep into this. Oh my God. Sorry.
Oh wow! Look at that. Okay. So what is this?
All right. That's an X, but Logan was bothering me. I didn't finish. Yes, it does have to do with self-control, but we're not doing that now. We're not doing right triangle trig. We're just doing trig. What? No. All right. So take a look at the graph there, and I'm not going to have you finding these points just yet. The one thing I do want you to notice is look at your x-axis. It looks a little different than a normal x-axis in that the units that it's going by. It looks like it's going. Yep. Every tick mark is a half of a pi. Every other one is a full pi, so I'm going from -2 pi to 2 pi, huh?
Is this still 0?
Just looking at this and doing nothing else but looking at it to analyze it. What is the domain of this function?
Negative infinity.
Negative infinity to infinity. Now, this is a sine, huh?
Oh, yeah.
For what? Now look, here's what you need to know about this. It continues doing this. It's a sine wave. It continues doing this forever and ever and ever. So it's continually oscillating like that. Huh?
What range?
Negative 1 to 1 inclusive, right? Because the points are actually there. So brackets from negative 1 to 1. Because those points are actually, it starts here and then it goes up and then it comes like this. So it does this. So it goes from negative 1 to 1. So x-intercepts. So this is going to be a pattern of numbers, right? If you look at what's happening, what do you notice? It's crossing the x-axis how often? All right, let's start because I think that we'll just stick easy with this and I'll show you how to write this fancy a little bit later. Let's do the ... on this one to save time. We start at 0, it crosses the x-axis. It crosses again at pi. It crosses again when? Look at your graph, look at your graph, look at your graph. 2 pi, and it continues on in both directions in that way, so every pi. I am going to show you another way to write out loud. I am going to show you. You could also write this as k pi, where k is any integer I want it to be. This is the way that it will be written for you and that pretty soon you'll be expected to write, so you might as well go ahead. Yes. K pi means take some number k and multiply by pi, and that's an x-intercept. What is k? K is any integer. So that means I should be able to look on my graph, and at 7 pi, it's going to cross over. At negative 3 pi, it's crossing over. Any number that I put, as long as it's a whole number in front of pi, then that's a place where it's crossing the x-axis.
What is this k?
You see what I'm saying? It doesn't matter what number you put in front of there, that's a place that it crosses the x-axis. I'm fixing to get to it. Y-intercept's just 0.
What about extreme? It doesn't have it.
Scott. It does, but this is saying every single integer. Every integer in the world with a pi hook to it is a place where sign crosses over. All right. That's x-intercept. Y-intercept we said was 0. Extrema. Extrema are highs and lows. Remember, they're maxes and mins. They don't have to be absolute. They could be relative also, right? This one has an infinite number of extrema. Remember the definition of extrema. I stop increasing and start decreasing, or vice versa, right? So does this graph ever do that? Yeah, an infinite number of times, right? I have an infinite number of highs and lows, right? So here's how I write it. For the maxes, what? Peasy. Why are you using a P?
Why are you using a K?
All right.
No, actually, why are you?
Where are they happening? Huh?
Why actually?
It's a racist one.
I'm just using a pair. I'm going to use K every time. All right, look. Where are your maximums happening? Look at your graph. That's not at 1.
Half a pi.
That's at a half a pi. It's pi over 2. Where does the next one happen? Actually,
No, the y-axis is over. What is that?
How does 0 comma pi, comma 2 pi equal k pi k equals 0? That doesn't make any sense.
Wouldn't the max just be fine? Because it doesn't matter how many places.
here's a max and here's a max. Do you agree? How far apart are those two maximums?
Several pi.
4 halves of pi. 2 whole pies. And do you agree that Logan, open the door. All right. Do you agree that that pattern continues?
Yeah.
Okay. Everything about this continues. So my maximums occur. Here's what. Stop it.
Get the camera.
I wonder when the last time a fight happened in the RS club. That ever happened?
I was shaking in my
Go,
boots.
go. Just write it this way. Shh, shh, shh. Look at scrap.
What's the better way to write it?
I'm not even going there.
Why?
Because
Can I see it?
I'll show it to you off the board.
Hold on, so it's
Off the
negative
record.
What is it? K pi K E Z Z or something?
All right. Shh, 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 shh. The maximums are occurring at these places. Now, the maximum value, though, think carefully before you answer this. Is my maximum absolute or relative? If maxes and mins are talking about height, they're, well, yes and no. There is an absolute highest point. There is absolute highest height. Yes. Yes. So there could be multiple absolutes if they're tied for absolute. Does that make sense? So what, because when we talk about absolute value, and this is a real important concept, when we talk about value, like if we say the max value or the min value, we're talking about y here. We're not talking about x. So what's the maximum value of the function? 1. What's the minimum value of the function? -1. If we're talking about where it happens, we're talking about x. So this is where, this is the actual value. Do you see the difference? So depending on what it asks you, now for these, it's just asking you where it happens. But I need you to understand the difference in where it happens and what it is, and why these are all actually absolute. Does that make sense? You tell me what you think you would do for the minimum. Negative, keep going, -1 pi over what? Yep, because it's a half a pi. Where's the next one? Yeah. Yes. Dot, dot, dot. Yeah, because each, that is a typical trig unit function. It goes by half pies. And it goes from -2 pi to 2 pi. Okay, so I'm going to do a U with this, okay? So whenever I talk about increasing, I'm going to just look at this for right now, and I'm going to start with the very first full increasing interval I see. Which one is it? Where does it start? We're talking about where, so we're talking about x. Negative. Okay. I'm going to actually start, I want a full cycle, if that makes sense, at -1/2 pi. So -pi/2 until what? Each tick mark is a half a pi. Because it takes 2. If I'm on this, if this is pi, then halfway in between would be a half of pi, which is pi/2. 1 pi/2. That is an increasing interval. Do you agree? Now, you can't see the next full interval on your graph, but you can infer what it is. I'm going to hook a U to it. Where does the next increasing start? Nope, look closely. Yes, 3 pi/2. Well, we exclude it because it's not technically increasing at the point that it turns, because it's a turning point. Now, how far do I need to go, do you think? Because this is all it's all the same, right? It's just a repeat of the same thing over and over. There's 2 pi in between here, so how do I get to the next one? Seven pi over 2, right? And I could just do this, dot, 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 u, dot, dot, dot. I knew this was going to be hard. This is always hard the first time you see it. Okay, so let me draw it out. Let me take it out a little bit further for you so you can see. And let me do it like this. Okay, it's okay. That might have been supposed to be 5. You might have been right to start with. Let me look at it. Yeah, this is a 5. Sorry. This would keep right on. Kind of, yeah. Okay, so think about it like this. 4 pi over 2, 5 pi over 2. The next would be 6 pi over 2, which is 3 pi. It's a half a pi for each one. 1 pi over 2, 2 pi over 2 would be pi. 3 pi over 2, 4 pi over 2. I add one more half each time I do it. Does that make sense? Or think about if I had a number line and this was 0, this was a half, this would be 1. This is 1.5, which is 3 over 2. This would be 2. What would this be? 2.5, which is a fraction, looks like what? One more. 5 over 2. So this is the same thing, but there's just a pi hook to it. Yes. So it's 1 pi over 2. Pi. 3 pi over 2. 2 pi. 5 pi over 2. I can see the reflection dim a little bit. So this one's always continuous. Discontinuities happen. We're looking for holes or jumps or asymptotes. Jump. It jumps every integer. Yes. All right, so decreasing. If I start looking at decreasing from pi over 2 to 3 pi over 2, do you agree? And then I'm going to join that with, I pick up at 5 pi over 2, and it decreases until I get to what? What do you think? 7 pi over 2. And I pick up to. This is hard. I know this is hard. We won't be doing this for every single one right now. I just want you to, okay. Not right now, man. Yes. Cosine's exactly the same, but everything has shifted a bit. So you have to look. I don't know. Not tomorrow. Bless you. Yes. Yes. You could. All right. Yeah. Yeah, we went a little long today. How do you know if it's even or odd? What does this look like to you? You think it looks even? I mean, look at, well, y'all don't know how to evaluate. So, look at this one. If I look at it this way and then I look at it that way, does it look exactly the same? Then it's odd. And look at the bottom one. Does it look the same upside down and right side up? No. Is it reflected in the y-axis? Yep, which tells me it's what? Yes, yes. Even, odd. I mean, odd, even, sorry. You could, but do you know how to find the sign of a number?
Logan does, because Logan took, what you call it?